So basically, this is our first and second part of organic chemistry, year one, where I'll be the second part of CLK is left out in another video, where we see the introduction to organic chemistry. Now, basically, we see that various types of definition, one-word answer definitions are asked. That basically what are, well, you can say either a structural formula or displayed formula or skeletal formula. What are they? What does it actually mean? Now basically a displayed formula, it shows every atom and every bond in the molecule. In other words, a single line being a single bond, a double line being a double bond, and a triple line being a triple bond. For example, ethene, or you could say propine or ethine, they all have these types of triple bond molecules. Then you can see the structural formula. Now basically the structural formula, what is a structural formula? Now, a structural formula shows the unique arrangement of atoms in a molecule in a simplified form, without showing all the bonds. Each carbon is written separately with the atoms or groups that are attached to it. For example, CHHH, CHHH is written as CH3CH3. Now basically this leads us on to our what is a skeletal formula. Now basically a skeletal formula is when we basically it's the notation of the carbon atoms that are basically they're not drawn. The carbon atoms are not drawn. Straight lines represent the carbon-carbon bonds, and carbon bonds are assumed to be where the bonds meet. Neither hydrogen atoms nor CH bonds are drawn. Each carbon is assumed to form enough CH bonds to make a total of 4 bonds, consisting of double bonds as 2. For example, then we move on to basically what is the now they've added in this very cleverly. This is from the bonding chapter. That notice that the skeletal in an unbranched alkanes chain, the bond angles are 109.5 degrees. Basically, this is what you need to know. Now, I've got another thing for you to observe is the three-dimensional analysis of the structural formula. Basically, now these attempt to show the three-dimensional analysis of the structure of the molecules. The bonds coming out of the paper are shown by wedge, in other words, a solid line. Now the bonds going into the paper shown by a dotted line. Then I'll show you an example. Basically, an example of this could be methane, for instance, or any such particular process. I'll just show you. For example, it could be methane, in which we could have the molecule, or rather saying in fact carbon tetrachloride, in which you can observe the solid wedge and the dotted lines respectively. Now we come to the reaction mechanisms. Now what are the reaction mechanisms? Well, basically that reaction mechanisms involve two distinct processes, which are curly arrows and free radicals. Now, first of all, we start with curly arrows. Now, basically, we can often explain what happens in organic reactions by considering the movement of electrons. Now, As electrons are negatively charged, they tend to move from areas of high electron density to a more positive charged area. For example, a lone pair of electrons will be attached to positive end of a polar bond, written as C delta positive. The movement of a pair of electrons is shown by a curly arrow, as I had told you in a video of the reaction mechanisms which we had done. The movement that starts from a lone pair of electrons or from a covalent bond and moves towards a positively charged area of a molecule to form a new bond. Now this is the second bit which we come to, which is our free radicals. Now basically free radicals sometimes in a covalent bond, which consists of a pair of electrons shared between two atoms, may break in such a way that one electron goes to each atom to originally form the bond. These fragments of the original molecule have an unpaired electron, and they are called the free radical. If you remember the free radical substitution which we had done in the case of ozone depletion, which I had added in our reaction mechanisms, that you can observe. Now basically coming on this, then we move to our process of our the nomenclature, in other words how the nomenclature takes place, on the use of our prefixes and suffixes, which I would just leave up for you now. Where we come to now the discussion of our functional groups. Which you can observe now. Where we come to the chain and position isomers. This is very, very important. You need to know the chain and position isomers. That how a chain and position isomer. This is very important. अक्सर questions में पूछे जाते हैं structural isomerism, functional isomerism, positional isomerism. इसमें ये पूछा था. So इसमें ये देखना कि ये कैसे होता है. In the sense कि ये जो 2-methyl pentene है, फिर 3-methyl pentane है, ये है हमारे पास क्या बोला? ये है हमारे पास एक है structural isomerism. Oh sorry, the positional isomerism rather. Then as you can see in the box to us how the alkane, alkenes, halogenoalkanes, alcohols, aldehydes, ketones and carboxylic acids are named respectively. Which moves us on to our next chapter, which is the alkanes. I'll be covering the following pieces of information in detail, then moving on to the laptop where I'll be continuing from the catalytic cracking processes. Basically, the general formula of alkanes, well, alkanes, as you know, it's saturated hydrocarbons in which they contain a carbon-carbon and carbon-hydrogen single bonds. इसमें कोई double bond देखने को नहीं मिलते हैं, और जिसके कारण they are among the least reactive organic compounds. They are used in fuels and lubricants and starting materials for a range of other compounds. This means that they are very important to industry, and their main source of, in fact, alkanes is crude oil. Now talking about the general formula. The general formula is in fact our CnH2n plus 2. Hydrocarbons may be unbranched, branched chain or rings. Now coming to the unbranched chain. Basically, unbranched chain are often called straight chains, but the C bond angle is 105 degrees. Now, for example, pentane. Now, seeing the branched chain. However, the branched chain example, as you can see, is methyl butane. As you can see in the ring alkanes are actually a general formula of H2N because the end hydrogens are not required. Now, basically, we come to then the isomerism bit. In other words, how the isomerism bit is considered. That basically methane, ethane and propane have no isomers, but after that the number of possible isomers increase with the number of carbons in the alkane. For example, butane with 4 carbon has 2 isomers, but whilst pentane has 3. Then we see our next process, so we come to the physical properties of our actual alkanes. What are the physical properties of our alkane molecules? Basically, we see the first particular property is when it comes to our polarity. Now, alkanes are almost non-polar because the electronegativities, carbon being 2.5 and hydrogen being 2.1, are so similar. Now, this in turn leads to only the intermolecular forces between the molecules are weak van der Waals forces, and the larger the molecule, the stronger the van der Waals forces. Which brings us on to the next point, which is our boiling point. Now, the increasing of the intermolecular forces is why the boiling point of the alkane increases as the chain length increases. The shorter chains are gases at room temperature. However, obviously pentane with our 5 carbons is a liquid with a low boiling point of 309 Kelvin. In other words, 36 degrees Celsius, as the chain length is about 18 carbons. Now, at a chain length of 18 carbons, the alkane becomes solid at room temperature. The solids may have a waxy feel. Then the alkanes in branch chain have lower temperature than the straight chain alkanes with the same number of hydrocarbons. This is because they cannot be packed together as closely as unbranched chains, and so the van der Waals forces are not so effective. In other words, this is very, very important. That why, with the case of increased branching, the boiling point decreases respectively. Which brings us on to the solubility on how soluble. In other words, the alkanes are insoluble in water. Basically, this is because the water molecules are held by hydrogen bonds, which are much stronger than the van der Waals forces that act between the alkane molecules. However, alkanes do mix with other relatively non-polar liquids. Now, how do alkanes actually react? In other words, what are the reactions with alkanes like? Well, basically, the alkanes are relatively unreactive. They have a strong carbon-carbon and carbon-hydrogen bond. They do not react with acids, base, oxidizing agents, and reducing agents. However, they do burn and will react with halogens under suitable conditions. They will burn in plentiful supply of oxygen to form carbon dioxide and water. Or you can say in a restricted supply of oxygen to form carbon monoxide or carbon. Fractional distillation of crude oil. Now, here we refer to the process of fractional distillation, how it occurs. Which brings us on the point of what is fracking. These are the various points of fractional distillation on which we obtain the following products. Carbon 4 to carbon 12 gasoline, petrol and naphthalene. This is used in the cars. And carbon 12 to carbon 15, this produces kerosene and paraffin. Obviously, the uses in jet fuel and lighting. Paraffin, in other words, the gas, which is paraffin lamps. Then you can see the carbon 15 to carbon 18, which leads to the formation of diesel and oil. See how it differs from carbon 4 to carbon 12 to carbon 15 to carbon 18 on how diesel oil and the petrol is formed, and particularly diesel obviously used in lorries and in boats. Moving on to carbon 19 to carbon 35, this is used in lubricating oils and in waxes. This forms rather, and use obviously in candle and in engine oil. Now, carbon 36 rather to 70, this leads to the formation of fuel oil. Their uses in the processes of the ships and power stations. Now, which leads us to basically the formation of our carbon 17 onward compounds. These form something known as the tar or bitumen. Now, bitumen is basically used in the cases of the road surfacing and for roofing. Now, basically what this leads us now, the bitumen products, although it's formed at basically high temperatures, because as the temperature rises, the products actually sink to the lower level of the distillation tube. Basically, the least temperature one, they actually go up on the distillation column, and the one which has the most temperature will be present at the bottom, be formed at the bottom. Now, this leads to the process of cracking. Now, basically, cracking occurs when, due to the formation of these basically large, long chain of the hydrocarbons, is basically the naphtha fraction from the fraction distillation of crude oil is a huge demand for petrol and by the chemical industry. The longer chain fractions are not as useful and therefore have low value economically. Now, most crude oil has more of the longer chain fractions than is wanted, and it's not enough for the naphtha production, which results in obviously the shorter chain products being more valuable than the longer chain. To meet the demands for the longer chain, for the shorter chains, many longer chains may be broken down to shorter lengths, hence the process of cracking. Now, as you can see here, I've noted the two processes of cracking: thermal cracking, which occurs at high temperatures, approximately 700 to 1200 Kelvin, with high pressures, approximately up to 7000 kilopascals. Now, basically, this process involves a long chain of our saturated hydrocarbon, which results in the production of the free radicals and which leads to the production of an alkene and a suitable alkane molecule. And the catalytic cracking, this is different as it involves a slightly lower temperature of 720 kelvins and a lower pressure as well. And this was zeolite catalyst. Basically, zeolite catalyst is basically it's a honeycomb structure, basically it's a honeycomb shape which increases the surface area, and this has an aluminium, oxygen, silicon framework respectively. Moving on to the combustion processes. Basically, combustion occurs in complete when oxygen supplied. It leads to the formation of carbon dioxide and water when the unsaturated hydrocarbon is burnt. Now, basically, the greater the number of carbons present, the more heat is input. For this example, for this reason, this is used as a fuel, which leads us to coming on to they allowed us to store a large amount of energy for a small amount of weight. Now, incomplete combustion. What's incomplete combustion? Basically, when limited supply of oxygen is supplied, supply of oxygen is present, the poisonous gas carbon monoxide, or CO, is formed. For example, in this reaction, even with less oxygen, carbon or soot is produced. The black, or you can say these are known as the carbon particulates. basically the carbon particulates formed. Now the flame is, for example, when a Bunsen burner is used in a closed air hole, the flame is yellow with a black sooty deposit appears on the apparatus. Incomplete combustion often happens with long chain hydrocarbons, which need more oxygen to burn as compared to shorter chains. Which leads us on to the polluting the atmosphere. Now, this topic is in your January mocks, so please listen to this carefully. Basically, the various pollutants present are carbon monoxide, nitrogen oxides, sulfur dioxide, carbon particles known as particulates, unburnt hydrocarbons, carbon dioxide, and water vapor. Carbon monoxide is a poisonous gas produced by incomplete combustion. Nitrogen oxides, namely NO, NO2, N2O4, abbreviated as NOx, are produced when there is enough energy for nitrogen and oxygen in the air to combine. For example, N2 gaseous state plus O2 gaseous state gives us 2 molecules of NO in its gaseous state. This happens in a petrol engine at high temperatures present when the sparks ignite the fuel. These oxides may react with water vapor and oxygen in the air to form nitric acid. They are therefore contributors to acid rain and photochemical smog. Sulfur dioxide is another contribution to acid rain. It is produced from the sulfur-containing impurities present in crude oil. This oxide combines with water vapor and oxygen in the air to form sulfuric acid. Carbon particles known as particulates, which can exacerbate asthma and cause cancer. These can lead to processes of respiratory tract infections or ailments. In other words, asthma and cancer as well. Unburnt hydrocarbons may also enter the atmosphere, and these are significant greenhouse gases. They contribute to photochemical smog, which can cause a variety of health problems. Which brings us on to our basically carbon dioxide, which is a greenhouse gas. It is produced when hydrocarbons burn. Although carbon dioxide is necessary in the atmosphere, its level is rising. And due to the increase in the levels of the carbon dioxide, this will lead to consequent climate change. In other words, global warming. Now, water vapor, which is a greenhouse gas. Now, flue gas desulfurizations. Basically, a flue gas is known as a wasteful gas, and in particular, we'll be talking about here that the formation. Well, basically, we're talking about sulfur dioxide and sulfuric acid and how it is removed. Basically, how is sulfuric acid formed? Now, the SO2 or the sulfur dioxide given out by power stations reacts with half a molecule of oxygen and a water molecule to give us the sulfuric acid.